Let's imagine a perfect math machine. You feed in any statement, and then it pops out true or false. Today, we'll speak about why that dream hits a hard limit. We'll see how self-reference, a clever coding trick, and a famous result from 1931 reveal that even our best formal systems have a hard limit and leave us with some truths that can't be proven. And we'll end with the implications of that on algorithms and computing. And now, in the early 1900s, David Hilbert put forward a bold agenda: make mathematics airtight. There's three goals to that: completeness, every true statement can be proven in principle; consistency, no contradictions. The system can never both prove a claim and its opposite; and decidability, there exists a general method or an algorithm to determine the truth or falsity of any given statement. If we can have all three, we could, in principle, build that machine we just spoke about. That ran into an issue. Enter Kurt Gödel. He created a statement, a Gödel statement, G, which is essentially says the statement is unprovable. If your system is consistent and powerful enough to express arithmetic, it cannot prove G. Yet, because it cannot prove G, G is true. So truth outruns proof, and then some truths become unprovable in the system. You might have seen the common quip, the statement is false, and that's the liar paradox. Gödel's version is more careful. It's not about being true, but about being provable inside a given system. And that precision is what makes this theorem rigorous and uh, elevates it beyond just some paradoxical wordplay. So uh, make how did Gödel make a statement talk about its own provability? He used something called Gödel numbering. Every symbol, formula, proof uh, gets a unique code as a natural number, and that way the system can use arithmetic to reason about its statements. For example, like a simple string like 2 plus 3 equals 5 can be encoded as a single large integer where each number and symbol represents some other number. It's basically like a barcode made of primes and exponents, and the exact number, the exact method isn't really important right now. The key idea really is that statements can become unique numbers and that arithmetic can now speak about those numbers. So that is about the proofs and the statements. So then what follows is extremely sobering. If your system is both consistent and strong enough for arithmetic, it cannot be both complete and decidable. There is no single algorithm which can settle all mathematical truths. Some truths will permanently be beyond any procedure that gives you an answer all the time. It's not a failure, it's just a built-in limit to mathematics. And computer science actually reaches a parallel frontier. Alan Turing showed that there is no general algorithm that, given any program and any input, can always decide whether that program eventually halts or runs forever. The spirit is very similar. There's no universal, infallible truth machine for programs either. This connects Gödel's limits on proofs with one of the fundamental limits of computation. So here's the trade-off we live with. In powerful enough systems, you can't have completeness. You can't have consistency. You can't have decidability all at once. If you insist on consistency, which we do because we don't want to prove a statement and its opposite, then we accept that some truths are going to be unprovable and that no single algorithm can decide them all. This doesn't really take away from math, but it deepens its character and shows us that there's always more to explore. That our methods are never complete. Yeah. Thank you.